Okay, in this video we're going to talk about transformations of the plane, and we're going to especially want to look at one-to-one transformations of the plane. So just to look at the definition, a one-to-one transformation of the plane is just a one-to-one function from one subset of the plane to the other subset of a plane. So in general, we'll let R be the range of this function, so this function is always onto, which means we'll never really need to check that it's onto, but we might need to check that it's one-to-one. And furthermore, it doesn't need to be one-to-one over all of R2, it only needs to be one-to-one for elements inside of G. And we'll check that with some examples so you'll see exactly how to do it. And so generally we call this thing T, and we'll write it as T colon G goes to R like that. And then furthermore, there's some other notation which we use from time to time, which is T evaluated at UV gives us XY. Or we could look at it kind of parametrically in this way. So x is a function of u and v, and y is a function of u and v. Graphically, what's happening is the following. We want to think of the domain here as living inside the UV plane, which is just a copy of R2, and maybe it looks like this blob, and an arbitrary point UV there gets mapped to an arbitrary point XY over here, and this region R is inside of the XY plane. And really what we're going for here is to eventually use this to change variables in a general way in double and triple integrals. And what we'll really want is to have one of these be pretty complicated and another one of them be simple. Maybe even a rectangle, which makes it as simple as possible. Okay, great. So let's look at our first example. So for our first example, we'll consider this region. So let's say R is equal to all points xy in the plane that satisfy the following. So we have x over 2 quantity squared plus y over 5 quantity squared is less than or equal to 1. Okay, good. So that's going over here in the xy plane, so I'll write it on the right. And notice that we can figure out what that is by covering up one variable at a time. So notice if we set y equal to 0, in other words, we cover y up, we'll get x over 2 squared is less than or equal to 1. But if we look at the boundary of that, that means x could be plus or minus 2. So just to reiterate, the boundary would be when x over 2 squared equals 1. Take the square root, you get plus minus 1. Move that 2 over, and you'll get plus minus 2. So that means here, let's say this is negative 2 and this is 2. So that means these points right here are on the boundary. Now we can do the same thing for the y coordinate. So cover up the x, and similarly we'll get y is equal to plus minus 5. So we could write that up here and then down here. Great. And then another thing to kind of keep in mind is that you may recognize this as the the equation of an ellipse, and that's exactly what we're getting here. So we're getting an equation of an ellipse where our minor axis has radius 2 and our major axis has radius 5. And so this outer boundary here is actually exactly the ellipse x squared over 4 plus y squared over 25 equals 1. And then everything on the inside is what we're calling our region R. Okay, so now what we'd like to do is pick a change of coordinates that makes that simpler. And we can do that by letting u equal x over 2 and v equals y over 5. So notice that's going to simplify this thing a little bit. So let's go ahead and do that. So we'll let u equal x over 2, and then v equals y over 5. So notice that's going to give us x equals 2u and y equals 5v, which means our transformation t takes uv to 2u 5v. So that's our transformation here. Okay, great. Now let's see what that region looks like over here in the UV plane. So notice if we replace x over 2 with u and y over 5 with v, that's going to give us exactly u squared plus v squared is less than or equal to 1 inside that equation right there. So what that tells us is that our region G in the UV plane is going to be given by UV such that u squared plus v squared is less than or equal to 1. But that's even a simpler region to get a handle on than the other one. That's just the unit circle. So here we can write u, v, and then we can go ahead and draw our unit circle. So that goes 1, negative 1, 1, negative 1 on the UV axis. And we can go ahead and shade that and name it G. And our function t is taking an arbitrary point here to a point in there. Okay, good. Now, let's go ahead and see if we can show that this is one-to-one. Okay, so just recall, how do we show that something is one-to-one? Well, what we do is we set t of u1, v1 equal to t of u2, v2. In other words, we try to show that it's not one-to-one, and then we'll end up with u1 equals u2 and v1 equals v2. So in fact, there's not much to do here because this function is so simple. Notice we get 2u1, 5v1 equals 2u2, 5v2. But notice that gives us these two equations, 2u1 equals 2u2, and 5v1 equals 5v2. Great, but dividing by 2 and 5 respectively will give us u1 equals u2 and v1 equals v2. In other words, our point u1, v1 equals our point u2, v2. Great, and that's all that we really need to do here. And another thing that we can do is look at the inverse function. So the inverse function isn't so hard here. We'll look at another example next where the inverse function is a little bit trickier. But notice our inverse function in this case, t inverse, so that needs to take on x and y values and give us u and v values. But notice we can just take this as 1/2 x, 1/5 y equals u, v. And that's just given by this kind of original substitution that we did. Okay, so what we've shown is that this is a one-to-one transformation from the plane to the plane. Okay, great. So I'll clean up the board and then we'll look at another example. Okay, so for our next example, we're actually going to start with the same region R in the x, y plane, but we're going to use some inspiration from polar coordinates to write a change of variables that changes this into a rectangle. So let's recall for polar coordinates you have x equals r cosine theta and y equals r sine theta, and that works really well because x squared plus y squared equals r squared. Now we can almost do the same thing here, but instead of having x squared plus y squared equals something, we have this x over 2 quantity squared plus y over 5 quantity squared equals something. Actually less than or equal to something, but as you saw before, we start off being most interested with what's happening on the boundary. So being inspired by that, let's go ahead and let x over 2 equal r cosine theta. And then we'll let y over 5 equal r sine theta. Great. And notice what that tells us is that x over 2 squared plus y over 5 squared equals r squared cos squared theta plus sine squared theta, which is equal to r squared. So it's just like polar coordinates. It's some sort of like deformed polar coordinates, if you will. Okay, great. So now notice we can write that as x equals 2r cosine theta and y equals 5r sine theta. Okay, great. So what that gives us is our transformation t, which goes from r theta. Those are our original variables, and it takes us to 2r cosine theta, 5r sine theta. Great. Now, notice that we have x squared plus y squared. So notice we have x over 2 squared plus y over 5 squared. That needs to be less than or equal to 1 by the definition of our region. So that means that r squared also needs to be less than or equal to 1, which tells us that r is going to be between 0 and 1. And you might say, well, wait a minute, wouldn't that be negative 1 to 1? But in fact, it's maybe best to only take positive r values. I should say non-negative r values. Okay, great. And then what about our theta? So we want, theta is still the angle from the positive x-axis. So in order to count every point exactly once, we can have theta start at 0 and end at 2 pi, but not include 2 pi. So we'll have theta goes between 0 and 2 pi. So we've got something like that. Okay, so great. I'm going to clean up the board and then we'll rewrite this transformation and see what the picture looks like. Okay, so on the last board we argued that t of r theta was equal to 2r cosine theta, 5r sine theta. In other words, x equals this first one, y equals this second one. Now the next thing we want to do is look at what this region looks like in the r theta plane. So notice we also argued that r needs to go between 0 and 1, and theta needs to go between 0 and 2 pi, not including 2 pi. So let's see. That means over here in the r theta plane, we have the following picture. So notice r can go out here to 1, theta can go up here to 2 pi, but notice it doesn't include 2 pi, so we can put a dotted line right there, and then we'll put solid lines all around. So we've got something like that going on, and then over here, this is our region which we've called G. Good. So our transformation takes that rectangle in the r theta plane and turns it into that ellipse into the xy plane. Okay, good. So let's go ahead and see if we can find the inverse transformation as well, because that's a good exercise for something a little juicier like this. So in order to find the inverse transformation, what we want to do is set t of r theta equal to xy and then solve for r and theta. So let's see if we can do that. That's going to give us x equals 2r cos theta and y equals 5r sine theta. Good. And then being inspired from this last step that we had, we noticed that that means x over 2 quantity squared plus y over 5 quantity squared equals r squared. Okay? But what that tells us is we can take r to be the square root of x over 2 quantity squared plus y over 5 quantity squared. And we don't need the positive and negative square root. Okay, so another thing that we can do is we can divide these two things. And notice if we do y over x, that's going to give us 5 over 2 times tangent of theta. Like that. So notice we've got sine over cosine, the r's cancel, and we've got 5 over 2. So what we'll have here is we'll have tangent of theta equals 2 over 5 times y over x. In other words, 2y over 5x, which makes theta equal the arctan of 2y over 5x. So we've got something like that going on, which means we can go ahead here and write our inverse transformation, which in terms of xy. So remember, the output of that would be r theta. So that's going to give us the square root of x over 2 quantity squared plus y over 5 quantity squared comma, and then the arctan. So we've got arctan 2y over 5x. Good. And that would be our inverse transformation. And then I'll leave it to you to check that this is one-to-one. It follows from the fact that the tangent function is one-to-one, kind of in the right spots. Okay, so I'm going to clean up the board and then we'll do one more example. Okay, so for our last example, we want to look at the following transformation. So we've got t of u v equals u squared minus v squared, comma, u times v. In other words, we've got these parametric equations, x equals u squared minus v squared, and y is u times v. And then we want to have G be the triangular region in the uv plane with vertices given by 0, 0, so the origin 0, 1, and 1, 1. So I'm going to go ahead and draw a picture of that. Good, so down over here, we want this point right here, which is, sorry, we don't need that point right there. We'll want this point up here, which is 0, 1. So I'll say this is the v-axis, this is the u-axis. So this is my point 1, 1. And then down over here, that's our origin. So we have this triangle that we're interested in here. Okay, so I'm going to go ahead and shade that in yellow. Okay, great. So I'm going to go ahead also and label these points. So I'm going to call this origin point P, this point up here point Q, and this point over here point R. And the first thing I want to do is see what my transformation does to these 3 points, and I'll call those points P prime, Q prime, and R prime. So notice T evaluated at P, so that's T evaluated at the origin, which gives me the origin, and so I'm going to call that P prime, and that's going to live over there in the XY plane. Now let's look at T evaluated at Q, so that's going to be T evaluated at 1, 1. So notice that's going to give me 0 for x and 1 for y. So I have 0, 1, and I'm going to call that thing Q prime. And then finally, T of R, so that's going to be T of 0, comma 1. So let's see what that's going to give me. That's going to give me negative 1 for x and 0 for y, and I'm going to call that point R prime. Okay, good. So that gives me this picture over here. So notice the negative part of the x-axis is more important in this setup. So we've got negative 1, 0. So this is my point R prime. So I'll write like that. And then I have Q prime, which is 0, 1. So that's up here. So I'll call that thing Q prime. And then the origin down here is still 0, 0. So I'll call that P prime. So those are my 3 points. Okay, great. Now what I want to see is what happens to these curves on the boundary. So let's label these curves on the boundary in the following way. So we'll have A, B, and C. And then let's look at them one at a time. So let's first notice that the curve A is equal to the line y equals x. So I shouldn't say y equals x because this is in the uv plane. This is the line u equals v. So here A is u equals v. Great. But now if we go ahead and plug that into our parametric equations for x and y, notice that's going to give us the following. That's going to give us x equals 0 and y equals u squared. Good. But now u goes from 0 to 1, so really we have x going from 0 to, x is staying at 0, and then y is going from 0 to 1. So in other words, we get this line right here. So this is given by A prime. So that's what we'll call the output of this. Okay, great. So now let's look at B. So now for B, what we have is we have V is fixed at 1. So v equals 1, and now notice that u ranges between 0 and 1. Okay? But now what that tells us that x equals, so we're going to get u squared minus 1. So u squared minus 1. And then we'll have y equals u. So we've got something like that. But now notice we can eliminate the parameter there, and what we'll see is that this is just x equals y squared minus 1, which is going to be a sideways facing parabola that's been shifted to the left by 1 unit. And another thing that we can see is that y will always be positive because y is equal to u, and u goes from 0 to 1. So what that tells us is that we get this top half of this sideways facing parabola. So that is our curve B prime. Okay, great. Now you can probably guess what our curve C prime is, but let's work that out. So notice on the curve C, we have the following. So we have U is identically 0, and then V is ranging between 0 and 1. So let's see what we get there. So that means y is going to be 0, and x is going to be negative v squared. So we get x equals negative v squared, and y is equal to 0. And then notice that x is going to be ranging between 0 and negative 1 in this case because we've got the minus sign out front. So that's going to close this loop up, and we can go ahead and call this thing C prime. Okay, good. Now we can shade this in like that, and maybe we'll call this region R. And that's how this transformation works. Now you can also check that this is one-to-one, and you can find the inverse, but it's a little bit trickier in this case, and we're not going to do that. Okay, so this is a good place to end this video.